Guys, today I'm going to be talking about something that we learned both last week and this week, which is the running time analysis. And I'm just going to do a quick review of the three methods that we learned using this one example that we went over in class, which is the multi-pop stack. Okay, so let's start. And first, let's clarify our goal. So we want to study the running time of n operations, including push, pop, and multi-pop. So we all know about push and pop, but for multi-pop, it's you can pop number like k elements from the stack, like the top k elements from the stack. And in this case, you can see it's like 3. So it's like 1, 2, 3, 1, 2, 3 here. So yeah, so what we call like this type of analysis is amortized analysis. And the first one we learn is aggregate. So aggregate analysis means we count the total time for like n operations by putting ourselves into like a worst situation. And here we know that the number of pushes has to be smaller than n, and we can't do more pushes. So the worst time sequence would be we first do n-1 push, and we do one multi-pop of size n-1. So this is roughly O2n, and that's like ON. As for formal accounting, we can see the table below, and we know like the real cost is like 1, 1. And for multi-pop, it would be like the smaller number between the number of elements left in the stack and the k that we pick. But for amortized cost, we repay. We pay before. So when we push an element, we know that later it might be popped, so we give it 2 instead of 1. But since we give it like $1 more, we put $1 more on the element, we can give 0 to both pop and multi-pop. And this is what we learned this week, which is called the potential function. And here we define the potential function as the number of elements in the stack. For push, the CI prime is going to be CI plus 1 because every time we push an element, there will be 1 more element in the stack. And pop is simply 0, which is easy to understand. And for multi-pop, the CI prime will be CI plus, again, delta F DI. And here it's going to be K because when we pop K elements, there'll be K elements less in the stack. And we do minus K here, which gives us 0. Therefore, the running time of n operations in this case is ON, and for each operation, the running time will be just constant, which is O1 here. Yeah, so thank you for listening. Have a good weekend.